In Chapter 3, Part 5, we're going to learn and kind of talk about using balanced chemical equations. So with a balanced equation, we can predict the amount of product that we should be able to make. So if we know what it should make and what we started with, we can figure that out. So let's think about this in terms of something that we've all encountered, or if you haven't, we can picture it, a grilled cheese sandwich. So and these are traditional grilled cheese sandwiches, it takes 2 pieces of bread plus 1 cheese is going to get 1 sandwich. So when we think about this, the balanced chemical equation, if we were to write this in something a little bit more technical, we would have 2 bread, we're going to call this solid, plus a cheese, also solid, is going to give us, with a little bit of heat, 1 S. We don't usually write the 1, so I'll erase that. And we have an S, which is also solid. So in this case, we can start to talk about how much do we make. So to predict the product, let's just say you come to my kitchen and I have 5 cheese. So we can predict how many sandwiches we need. We have 5 cheese, and then we're going to use our stoichiometric ratio of 1 cheese makes 1 sandwich. So therefore, with 5 cheeses, we can make 5 sandwiches. So the stoichiometric ratio is the ability to use the coefficients that we see here for every compound in this equation. So the stoichiometric ratio in this case tells us the ratio of, in this case, bread to cheese. So we know when you make a sandwich, usually there's 2 breads and 1 cheese. So what about if we had instead, let's just say we have 15 bread. So you have 15 bread multiplied by 2 breads and 1 sandwich. That's going to give you 7.5 sandwiches. So we could do this for any components, and we could do this really for any set of equations that we think about. So let's look at this equation, and let's start to think about this in terms not just of bread and cheese, but let's think about this for a chemical equation. So how many moles of water are produced if we start with 1.57 mole of O2? So we have an equation, and in this balanced equation, it takes 2 moles of hydrogen gas plus oxygen gas, gives us 2 moles of water. So in this case, our stoichiometric ratios, they're these numbers here, and we're going to use those in our equation. So now we're going to start to use dimensional analysis, and we're going to say if we have 1.57 moles of O2, we want to convert that. So for every 1 mole of O2, we get 2 moles of H2O. And so when we plug this into our calculator, we get 3.14 moles of H2O. So in this case, we can convert moles to moles. Well, we know, and we've already talked about how to convert grams to moles or moles to grams. So let's do the same calculation, but now we're going to start with 25 grams of hydrogen gas. So we're going to take our 25 grams of hydrogen gas. Now we're going to use the molar mass. And so 1 mole of H2 gas is 2.02 grams of H2 and 1 mole of H2. Now we need to use our stoichiometric coefficient. So we know that there's 2 moles of H2 for every 2 moles of H2O. And so we can plug that into our calculator and get 12.376 moles of H2O. We need to double check our sig figs, and so the problem only gives us 3, and so when we use our sig figs, it's 12.4 moles of H2O. And you could have gone and converted into grams. You could have added on one more step. So here we could have also multiplied by in 1 mole of H2O, there are 18.02 grams of H2O. Now, a couple of things when we start to look at any of these components. We're going to start using lots of things. We're going to move from grams of hydrogen gas to grams of water or anything else. So it's my suggestion that we start to add as many of the units as possible. So all of these, so that we could then go back and cancel them out and we can make sure we get to the right thing. Because you'll notice, and what we'll see on a lot of these, is that sometimes the molecular weight is on the bottom and sometimes it's at the top. So the more you write down, the more likely you are to multiply in the right direction. So in this case, we have the combustion of butane. So this molecule right here is butane. And so if you remember butane, or in any combustion reaction, it's the combustible component plus oxygen gas plus, and that yields water and carbon dioxide. So what mass in grams of CO2 is produced from 1 gram of butane? So we're going to set this up. So we're going to have our 1.00 grams of C4H10. And that is 58.14 grams of C4H10 and 1 mole of C4H10. Now we need our stoichiometric ratio. So for every 2 moles of butane, that gives us 8 moles of CO2. So 2 moles C4H10. That gives us 8 moles of CO2. Now we want to convert to grams because it asks for this in grams. So in 1 mole of CO2, it is 44.01 grams of CO2. So then when we plug all this into our calculator, we get 3.03 grams of CO2. So this would be our final answer. So a couple of things when we think about this. The easiest places for us to really get confused are if we forget to use our stoichiometric ratio, right? So the stoichiometric ratio right here is found here and here. And so if you write down all of your units, we can really see how the grams of butane are canceled by the converted into moles of butane. Now you could do this in a series of single step calculations or multiple step calculations, but now we can convert from grams to grams. So in another example, we note that hydrofluoric acid, or HF, can't be stored in glass bottles because the silicates in the glass are attacked by the HF. If there are 0.45 grams of sodium silicate in a glass bottle, how many grams of HF will dissolve the silicates in the bottle? So the first thing we want to note is that sodium silicate is this. And so we're trying to determine what the balanced equation is here. So the first thing we want to do is start writing stuff down. So we're going to take our 0.45 grams of Na2SiO3. We're going to convert that using the molecular weight. So we're going to go ahead in this example, we're going to write out the molecular weights. So as a reminder, we calculate molecular weights by totaling up the different atomic weights. So for sodium silicate, Na2SiO3, that's equal to 2 times 22.99, plus for silica, it's 28.09, plus 3 times 16.00, and that gives us 122.07 grams per mole. And so for HF, it's 1.01 plus 18.91, and that gives us 19.91 grams per mole. So now we can use that information in our calculation. So we're going to use the molecular weight here of 122.07 grams. and 1 mole of sodium silicate. So now we need our stoichiometric ratio. So we're not actually converting reactants to products. We're actually figuring out reactant to reactant. So you can convert anything on the left to anything else on the left, or anything else on the left to anything on the right, and vice versa. So it is 1 mole of sodium silicate for every 8 moles of HF, and then 1 mole of HF. That is 19.91 grams of HF. So from here, we can now plug this into our calculator, and when we do that, we get an answer of 0.59 grams of HF. So this would be our final answer with the correct number of sig figs. So what we can see is that you can convert products to products, which is not what we did. In this case, we did a reactant to reactant, but you can convert anything else to anything else. So in this next example, we want to look at solid lithium hydroxide is used to remove carbon dioxide exhaled by astronauts in space. The lithium hydroxide reacts with carbon dioxide to form solid lithium carbonate in liquid water. How many grams of lithium hydroxide are required if 250 grams of carbon dioxide is exhaled by the astronauts? So this example is totally different. It doesn't even have a balanced chemical equation, but we can use the skills we've already learned to write the equation. So it says that lithium hydroxide reacts with carbon dioxide. Okay, so LiOH, it tells us it's solid, plus CO2, and that's a gas. And it's going to make lithium carbonate, which is Li2CO3, because carbonate is the CO3 2 minus, and that's going to give us a solid, plus liquid water, which is H2O, liquid. So we should double check if this is balanced. So there are 2 lithiums on the right side, so we'll drop a 2 here. So now we have 2 lithiums and 2 hydrogens, 2 oxygens. So far that looks totally balanced. So now we have a balanced chemical equation. So now we can go in and do what this is asking us to do. So we're going to take our 250 grams of CO2. And so we're asking how much lithium hydroxide do we need? So we're going to convert the CO2, which is one reactant, to the other reactant. And so the molecular weight of CO2 is 44.01 grams in 1 mole of CO2. Based on the equation, there is 1 mole of CO2 for 2 moles of lithium hydroxide. And then we want to convert from 1 mole of lithium hydroxide, and the molecular weight of that is 23.95 grams. So here we can go ahead and plug this into our calculator and get 272.1 grams of lithium hydroxide. So in any of these examples, if we have a balanced chemical equation and the molar masses, we can convert reactant to reactant, product to product, to anything else we want to think about.